So the next question is jumping jack, and we're getting some information about jumping jack here. He's jumping upwards at a velocity of 3.8 meters per second, but we actually have a number of other variables that are not given here but that we know. So we know that when someone jumps in the air, if they're a projectile, they're going to be accelerating towards the ground at 9.81 meters per second. So maybe I'll start putting these over here. So the vertical velocity initially going up is 3.8 meters per second, and the acceleration upwards is negative 9.81 meters per second. We also know that if Jack jumps upwards, at his peak height, his velocity final going up is going to be 0 meters a second. So that's to say, between his jumping up and jumping down, there's a point at which he's going to have a vertical velocity of 0, so if one transitions from positive to negative, and that's his final velocity going up. So we know this information here, so when we're asked about how long it would take Jack to reach his height, or what time that would be, we can start to use the laws of constant acceleration. In particular, the first law of constant acceleration is VI equals, sorry, my mistake, VF equals VI, add a t. And so the final velocity here is 0, and the initial vertical velocity is 3.8 meters per second, and that's added negative 9.81 multiplied by t. Now this just turns into a negative if it's add negative, and so we're going to add 9.81 to each side, and then we divide both sides by 9.81 to leave t by itself, and so we end up with 0.39 seconds. So that's the time that it would take Jack to reach his peak vertical height. In section B of the question, we're asked to what would be Jack's vertical displacement upwards, and so again we're dealing with the final velocity being 0. We've got the same acceleration, the same initial vertical velocity. We also know the time now, so in the laws of constant acceleration there's really one unknown, which is displacement, and we can use that. I tend to use the third law of constant acceleration for this one because I don't have to rely on the time I've already calculated, just in case I've made a mistake here. So that third law of constant acceleration is Vf squared equals Vi squared add to As, and in this case Vf is 0, and 3.8 is the initial velocity, so that's squared, add 2 times 9.81 s. Now there's a few steps of algebra there that I'm going to skip through a little bit here for the sake of time, but if you do those steps you should get something close to 0.74 for displacement up. So it's really just figuring those out and changing around the formula. Now the section C, if Jack landed on the ground with his knees bent, or 0.4 meters below his takeoff height, how long would he spend in the air total? Well, this is the one that takes a little bit more problem solving, because if we think about Jack taping off up to a certain point, and then he has to, so that is his up, and then his down is going to end up being 0.4 meters below what he started at. So this is going to be 0.4 meters. And then we need to figure out how long he would spend in the air going down. Now what do we know about this downward flight? Well, at the moment we know that Vi here is 0. So just like final velocity going up is 0, initial velocity going down is 0. We know that the acceleration is again going to be negative 9.81 meters per second. We don't know what the final velocity is, and we don't know what the time is. The other aspect is displacement. Now we don't know what the displacement is going down here straight away, but what we can start to look at here is the displacement up was 0.74. So if we know displacement up was 0.74 and the displacement from where he took off to the bottommost point is 0.4, we can just add these together to get the total displacement down. So the total displacement down between these two would be 1.14, because it's 0.4 add 0.74, and that equals the displacement down. Now if we know the displacement down now, and we know acceleration, we know initial velocity going down, now we have enough to figure out time. So I would use the second law of constant acceleration, and so that one is displacement equals VI t add 0.5 or half multiplied by negative 9.81 t squared. Again, a few steps of algebra here. Sorry, in that equation there I've actually mixed in answers and equations, so we'll write that out in full here. So S equals VI t add 0.5 acceleration time squared. So we'll forget that one for now, and the displacement is 1.14. Our initial velocity going down is 0, so this whole thing is going to be 0. Add 0.5 negative 9.81 t squared. Again, some short steps of algebra, but you should end up getting a total time down, that is, of 0.48. Now if that's our time down, we can add that to our time up, which we initially calculated over here, as 0.39, and if we add those two together, time up add time down equals total, which is equal to 0.39 add 0.48, which is then going to be equal to 0.87 seconds.